Evidence of neutrinos. Early in the 20th century, scientists had a problem with beta decay. For a particular isotope, every beta decay should release the same amount of energy. Therefore, if we were to plot a graph of the number of beta particles against the kinetic energy of that particle, we should get something like this, with all the particles for a particular isotope having exactly the same amount of kinetic energy. Experiment showed this not to be the case, and this is a graph of what we actually saw, with a significant number of particles having virtually no kinetic energy, leading to a maximum number of particles with a small amount of kinetic energy, tailing down to a maximum of kinetic energy here. This is the level of kinetic energy we would have expected from all the particles. In 1930, Wolfgang Pauli suggested that perhaps there was another as yet undetected particle that could be sharing the energy and the momentum of the beta decay, a little bit like this. The nucleus itself has recoiled and it has ejected the beta particle, or electron, and also the undetected particle, which Pauli named neutrino, or little one. Must be little to have been undetected at the time. In fact, it was later found that beta decay actually ejects an electron anti-neutrino. The range of energies of the beta particles can now be explained like this. In this animation, both the beta particle and the neutrino shared similar amounts of energy. However, what we could do is have this situation, where the beta particle has a small amount of energy, the neutrino taking the majority. Alternatively, the beta particle could take most of the energy with a small amount for the neutrino. We could clearly have anything in between. Alternatively, the beta particle could take most of the energy with a small amount for the neutrino. We could clearly have any situation in between these two. The neutrino was finally discovered 30 years later in 1956 by Raines and Cowan. It proved quite elusive for a long time. It was initially thought that the neutrino had zero mass, but recent experiments suggest it does have a very small mass. Around 10 to the 12 neutrinos pass through you every second, and from the neutrinos created in nuclear reactions in the Sun, many hit Earth. The vast majority pass straight through the Earth without any interaction whatsoever.